Before 1 minute, I am just opening the with armature resistance, shunt resistance, voltage, everything is given. So the objective is, as the x-axis load is increasing, how the efficiency will change. This is the objective of the doing that exercise. Then I have just written efficiency is output by input, so output by input plus losses. Then all that after substituting, I get this expression 230i by 230i plus this one, and we formed a plot for this, and we know problem. Then another problem we looked at in the last class was about again the losses in a DC generator, and two important diagrams are and another one is the power diagram that you are seeing on the screen. So there are three stages of power. So input power, then friction and iron losses. These are mechanical and iron losses, and then we have the power developed, and then copper losses. Finally, we have the output. So using these two figures, the circuit diagram and the power diagram, we are able to solve different problems. You had time to review this problem after the last class. Then we had a small derivation condition for maximum efficiency. So in which, after deriving, finally what we come to know is, if I consider variable loss equal to constant loss, then maximum efficiency is achieved. And then the condition, what is the current for maximum efficiency, also we had derived. So again, based on that, we had solved one small problem. So this was about one topic. Then apart from this, in the last class, what we had done, we had some small time to discuss about the working principle of a DC motor. So this is what I was explaining, working principle of a DC motor. So as you can see on your screen, so what you have is a north pole and south pole, and then a field winding that's separate, and then armature winding, and how it works. Anyway, so I'll once again discuss this today in today's class, and today we'll further continue on this. So maybe I'll give you just 1 or 2 minutes time. If you have any doubts in the previous class, feel free to ask now. You can either directly speak over the mic, or you can use a chat window to give your doubt. So we'll discuss that. Meanwhile, let me create the new file for our today's lecture. Topic of armature reaction in DC machine in today's lecture. But before going to this, there are some important interview questions. So imagine that you go for interview for some kind of electrical related company. So some of the questions that can be asked is, so these are basic questions. So first one is something like, explain working principle of DC generator. So this can be one question. So another question is, explain working principle of DC motor. And another important question can be, explain armature reaction in a DC machine. So first one, I'm sure you're comfortable with the first one. Second one also briefly we had discussed before. And third one is what I'm going to talk about today. So before we go forward, just take 2 minutes time, think about this. Suddenly you are in an interview and the interviewer asks you, explain working principle of DC generator. Can you explain? Yes or no? Similarly, explain working principle of DC motor. Can you explain? Do you know the working principle of DC motor? How it works? So again, finally explain, because without knowing these two, you cannot understand armature reaction. So that's why before I start, I'm just asking you whether you know one and two. So just take 2 minutes time. Just think about yourself. Try to discuss with your friends in your class and all. Do you know the working principle of DC motor, how it works? So just think about it. So I'll give you some time to think about it. When conductor cuts magnetic field, so this principle, this is used in DC generator. When current carrying it experiences force. Right? So this one is used in DC motor. So I hope you are clear with these two topics. So when a conductor cuts magnetic flux, EMF is induced in it. When a current carrying conductor is placed in a magnetic field, it experiences a force. So these two are nothing but the working principles for DC generator and DC motor. So now let's come to this concept of armature reaction. So now armature reaction is occurring in a DC machine. That means there is armature reaction in DC generator, there is armature reaction in DC motor also. So both places there is armature reaction. So but let us first discuss armature reaction in a generator. So what is armature reaction in a DC generator? So you have north pole and you have south pole and you have the armature in between. This is the armature and the armature has armature conductors. So what will be the magnetic field? So consider only field poles, field from poles. So then, so this, let's say this is a north pole and this is a south pole. Then if you consider only the field from the poles, it will be like this. So what is the direction of the field? So the direction of the field is like this. So let's represent this as Fm. So Fm is the main magnetic field. So this Fm is occurring inside the core of the armature. Okay, so this is considered only the field from the poles. Now, what happens in the conductors? In the conductors also there is a current flowing. So let me show that now. Next. So, so again this is north pole. Again this is south pole. Now again this is the armature. Inside the armature there are conductors. Now how the conductor current is collected? So because it's a generator, so there will be a brush here. So of course the brush is connected to the commutator, but for the simplicity of explaining, I am just showing that the brush is connected to the armature directly, but it is actually connected. This is the position. So I have one wire here and I have another wire here. So this is the starting point of the armature and this is the ending point of the armature, and I have the armature winding in between. So this machine is rotating, but the flux, the brush position is fixed constant. So like this. Now what is the direction of the current? So let us represent the direction of the current. So current direction I will represent by cross mark here. So whenever there is a current carrying conductor, the current carrying conductor will have a magnetic field. So this is again cross. So whereas this one is dot. So what is this notation? So like if I have current, if I have a conductor and then I have a cross, so this means current flowing into the blackboard. So the current is flowing perpendicularly into the blackboard. Then we use this cross symbol. Similarly, this dot symbol we use symbol for current flowing out of the blackboard. So this is the into the blackboard and this is the out of the blackboard. So these are the symbols that we are doing. Now what will be the direction of the magnetic field? So for this, if the current is flowing into the blackboard, the direction of the magnetic field will be clockwise, like this. So this, how do you know? This by applying the corkscrew rule. So if there is a screw and if you want to send the screw into the blackboard, you will rotate the screw in this clockwise direction. So this is the direction of the clockwise direction of field due to current. So now whereas if there is a dot, so let me draw that again. If there is a dot, then the direction of the current will be anti-clockwise, like this. So this is anti-clockwise. direction of the field. Now understanding this, now if I go back here, now all these conductors are placed nearby each other, and then all these dot conductors are placed nearby each other. So there will be a combined magnetic field because of the armature. So let me draw that. So the magnetic field because of the armature will look something like this. So clockwise direction here. So it will go up. So here it is up and here it is down. Let me draw one more line. So again here it is up and here it is down. Similarly, you look at this dot conductors. Here the magnetic field will be down again. I mean anti-clockwise. So when you have anti-clockwise magnetic field, so again here it will be down and here it will be up. Again here it will be down and here it will be up. So if you look at the core of the magnetic pole, so always the field is downwards inside the core of the armature. So inside the core, the magnetic field is always downwards. So what is the resultant magnetic field is like this. So this one we call it as FA because this is downwards. So now at the same time there are two magnetic fields. So if you go up here, first we have magnetic field of the poles which is FM, main magnetic field. Second we have magnetic field due to armature. This is the armature magnetic field. So let me show both at the same time. So now on your screen you can see at the top there is a main flux, at the bottom there is the armature reaction field. Now what is the combined resultant of these two? So you see, so Fm is the main flux and then Fa is the armature reaction flux. As a result, the Fr is the resultant flux and that will have a small angle like this. It is not exactly horizontal, it has some small angle going downwards. You can actually see it here also in the diagram. So what happens here, you see the flux lines are going upwards in the air gap. That means the main flux is diverted slightly upwards. And then here you see the flux lines are again going upwards here, but then in the middle it will be downwards. So as a resultant, so you see, let me draw that here. Resultant magnetic flux. It is a combination of both armature flux and the main flux. So it will be like this. This is the field. And if I draw vertical line, this vertical line is called GNA. This is geometrically neutral axis. But as a result of the both interaction of the magnetic fields, the resultant magnetic field. So this is the resultant magnetic field that is set up in the phone. So the direction of the field is like this. FR. So what is the effect of this? So this is the main field Fm, and this is the armature reaction field Fa, and this is the resultant field Fr. Now Fr is not exactly horizontal, so it has some small angle. So you can draw one more axis such that this axis is perpendicular to the magnetic field Fr. So therefore this angle theta m, it is denoted as theta m, and this line is called MNA, magnetically neutral axis. So this is the effect of armature reaction. So what is the effect of armature reaction? See, one thing you can see here, there is some cancellation. So you look at the top here, there is some demagnetization effect. So let me write that here. What are the effects of armature reaction? So one is demagnetization. So which actually means nothing but weakening or reduction in the main field. And the second effect is cross magnetization. This is nothing but distortion of magnetic field. So far, any doubts, any questions you have? Please take a couple of minutes time. I have explained what is the effect of armature reaction, and then I have explained as a result of armature reaction how the field will be. So this is the field without armature current. This is only the field because of armature current. And what you are seeing now on the screen, this one is the combination of both. As a result, the flux is traveling at an angle of theta m, and the theta m is a magnetically neutral axis. It's not exactly coinciding with the geometrical neutral axis. And then here you see the higher is the load, the stronger, more is the armature current, and stronger is the armature reaction. Therefore, higher is the angle of theta m. Let me write that also. Note. Armature reaction depends on amount of load or magnitude of load. So higher load, so this is basically electrical. Higher armature current this results in higher armature field. So the field is Fa. So this result in higher effect of armature reaction. So I'm just getting a call. And this in turn will result in higher shifting of MNA from GNA. So this is again very important thing to understand. So any doubts so far, whatever I've explained? So feel free to ask your doubts if you have any. I'll just give you 1 minute time to 1 or 2 minutes time to just review what I have explained before. And if you have any doubts, feel free to ask them. What is cross magnetization? So sure, let me try to do that. So what is cross magnetization? Now you look at it. Uh, so a doubt. So this is doubt asked by uh, JNTU KUCEV. Okay, so what is cross magnetization? And I will also add one more doubt. What is demagnetization? So what is happening is, see, the resultant flux. This is resultant flux. So now if you see, uh, basically, so therefore, if I take the components, so this is one component and this is another component. So the horizontal component is like this and the vertical component is like this. So this one is actually useful flux, but length is reduced. So you will notice that the resultant flux, if I just take the horizontal component, it will be slightly smaller. So therefore, this effect we are calling as demagnetization, reduction in the magnetic field. Now look at this one. This is F. Let's say this is cross magnetizing. So because of the resultant flux rotating by angle theta, the cross magnetization means the main flux is like this, the armature flux is like this. So this is a crossing. So because of this crossing, the field is distorted. So the distortion is called cross magnetization. So I hope you got this explanation. So the resultant flux is, there are two effects are there. So what are the two effects? So one effect is demagnetization effect and the second effect is cross magnetization effect. Now how to remedy this? So I think you know the meaning of word remedy. So remedy, like home remedies you have. So if you have some cold or something, you have to take some home items, something like that. So this armature reaction is a problem and how to solve it. So, so for demagnetization, use interpoles. So what are interpoles? So interpoles are nothing but, I'm sorry, not interpoles. I'm sorry, for D, so let me just use extra ampere turns in the main field. So if I initially generate a higher field, then the demagnetization effect will slightly reduce it, thereby coming to the correct size. So correct magnetic field. So that is the effect of this one. So usually series field winding, because armature series field winding will carry the same current that in the armature. So therefore, as the armature current increases, the armature reaction increases, but at the same time, magnetization like this. So for cross magnetization, so we can use interpoles. So these are poles between the poles, just that, just to reduce the distortion. So these are to reduce distortion in the magnetic field. Another thing you can do is shift the position of brushes to MNA. So instead of locating your brushes on the geometrically neutral axis, you can keep your brushes on the magnetically neutral axis. Okay, so enough of theory. Let us do some kind of derivation. So what is the derivation? So let's do some calculation. So expressions for demagnetization and cross magnetization, ampere turns. So let's do some derivation. So even before we do this, there is something I would like to explain first. So that is, you have this armature, and then I can just show the conductors like this. Then I can have vertical line like this. This is geometrically neutral axis. Then I have, let me show like this. Magnetically neutral axis. And then this angle is theta. So the same angle theta, I can consider the other side also. And what I can do is, so this angle is again theta m, theta m. So theta m is the angle of shift, mechanical angle of shifting of the poles. So look at this. So here it will be all cross. So here also it will be cross. And here it will be dot. Because these conductors are in the south pole and these conductors are under north pole, and this is the magnetically neutral axis. Now the field due to all of this will be something like this. So this field will be, I am only considering interested about the field because of the only this under this angle 2 theta, what are the conductors? Okay, so what is the direction of this field? Again, if you apply the corkscrew rule, so you can get the direction of the field will be like this. This one here inside the core, the field direction is like this. So here also you notice, if I draw the field will be like this, anti-clockwise. Anti-clockwise. So inside the core, the direction of the field is always from right to left. So this is like this. So this is nothing but demagnetizing field. So there is one more way of representing it. So this is FD. FD. So what is the main field? So the main field is coming from like this. I'm sorry. This is the main field. You see, main field and demagnetizing field are opposing each other. So that is because of the conductors which are placed in this angle theta m on either side. Similarly, now look at the field due to this cross. So again here it will be clockwise. So inside the core, the field is downwards. Similarly, here it will be anti-clockwise. Here also it will be anti-clockwise. So inside the core, the magnetic field is downwards. So this is FC. So FC is cross magnetizing. So what is the total field? So I have FM is the main field. This is FM. From the FM I subtract FD. Then I add, then to that again I'll subtract or I'll add the cross magnetizing field. Then finally you get the resultant field. So this is your resultant field, FR. So the same thing effect we had seen before also. So this is what is the resultant field. This is demagnetization and cross magnetization. So what you notice is demagnetization is caused because of the conductors placed in the 2 theta angle here. So that will be useful for derivation. So any doubts regarding this? I'll continue the derivation shortly, but meanwhile if you have any doubt you can ask on this. So here Z is total number of armature conductors. IA is armature current. I is current in armature conductor. So if you notice, IA and I are not equal. Armature current is not equal to the current in the armature conductor. Actually, because there are parallel paths. So I is nothing but IA divided by number of parallel paths. So A equal to 2 for wave winding and A equal to P for lap winding. So you know this. So then what I can do is total armature conductors causing demagnetization. So what are the total armature conductors causing demagnetization? So if you look at the diagram which I drawn before, the armature conductors causing demagnetization are are confined to this theta m, 4 into theta m. So there is theta, theta, and theta here and theta here. So the 4 theta will be the armature conductors that are causing the theta that are causing the demagnetization. Out of the entire 360 degrees, this total angle is 360 degrees, but I am only interested in those conductors which are falling in the 4 theta m angle. So if I have to derive it, so what I can do is I'm sorry. What I can do is simply I can take 4 theta m divided by 360 degrees. So this is a fraction. This I will multiply with the total ampere, total number of conductors, Z. So this is total armature conductors causing demagnetization. So now if I say total turns causing demagnetization. So what is the total turns? So these are conductors, turns will be divided by 2. So that's nothing but 4 theta m by 360 Z by 2. Then what I can do, this is demagnetizing. Then total ampere turns causing demagnetizing. So how to convert turns into ampere turns? Just multiply by I. So 4 theta m by 360 multiplied by Zi by 2. So this is the total ampere turns causing demagnetization. This is for the machine. So but then there are two poles. So per pole, so ampere turns causing demagnetization per pole is nothing but this entire thing 4 theta m by 360 into Zi by 2 into 1 by 2 because there are two poles that we considered. So now if I simplify, it will be just like this. So I'll get theta m Zi by 360. This is ampere turns causing demagnetization per pole. So this is important formula that we are getting. So to know the ampere turns causing demagnetization, first you should know how much degrees the angle is shifted and then the number of conductors and the current in each conductor. Now, how to calculate ampere turns? Causing cross magnetization. So just if I write total ampere turns per pole will be nothing but Zi divided by 2p. Why? Because Z by 2 is turns and then Zi by 2 is ampere turns. Per pole means I have to give 2p. So therefore, so this is 1 and this is 2. Ampere turns causing cross magnetization per pole will be is nothing but 2 minus 1. Total ampere turns per pole minus ampere turns causing demagnetization per pole. So that will be Zi by 2 360. So simply this is nothing but Zi into 1 by 2p minus theta m by 360. So this is the formula for ampere turns causing cross magnetization per pole. So this is about total about armature reaction and what is the effects of armature reaction, and we have also calculated the demagnetization and cross magnetization effects. So just briefly review this a little bit. Meanwhile, I'll prepare one question and we'll try to solve that question. So let me give you one small example problem. So this again I'm getting it from a textbook called BL Tereja Electrical Technology Volume 2. This is exactly example 27.3a. So anyway, so that given data is like this. 4 pole wave wound motor has 880 conductors. So load current is 120 amperes. So which can be assumed to be armature current also, because the field current is not given in this. So brushes have been displaced by 3 degrees from GNA. So that means theta mechanical is 3 degrees. So determine, this is given data. So determine ampere turns causing demagnetization per pole, ampere turns causing cross magnetization per pole, and finally additional field current for neutralizing. So field current for neutralizing effect of demagnetization. If there are 1500 turns in the field, turns per pole in the field. So this is the entire question, as you can see on your screen. So the given data is there and what you need to find out is there. So this is like typically the problem of armature reaction. So what you can do, so first thing is, first find out the I. So total load current is 120 amperes. So in wave winding, number of parallel paths is 2. So I equal to IA by 2. That is 120 divided by 2, that is 60 amperes. So this is basically the current in each armature conductor. So I am what I am getting. So then once I have this, rest of the thing is basically straightforward. So that is ampere turns causing demagnetization per pole is nothing but theta mechanical by 360 degrees into Zi. So that is nothing but 3 by 360 into, so how many conductors are there? So if you notice 880 conductors are there. 880 multiplied by 60 amperes. So this will give me a number of something like 440 ampere turns. So like this, I get the ampere turns causing demagnetization. Ampere turns causing cross magnetization per pole. The ready-made formula, that is, I have the formula just derived above. Theta m by, I'm sorry, 1 by 2p first, 1 by 2p minus theta m by 360. So number of poles are 4. So I'm using this formula. I get Zi 880 into 60 into 1 by 2 into 4 minus 3 by 360. So this is the entire calculation. And if you do this calculation, you will be getting some result as something like 6160 ampere turns. So this much of ampere turns are there for cross magnetization effect. Now, the third part of the question is additional field current for neutralizing the effect of demagnetization if there are 1500 turns per pole in the field. Okay, so how many ampere turns is required for demagnetization? 440. So 440 the additional current in field is nothing but this 440 divided by number of turns, that is 1500. So this will be something like, let me do the calculation. So 440 divided by 1500. So I'm getting 2.93 amperes. I'm sorry, 0.293 amperes. So therefore, this is the additional current required in the field winding to strengthen the effect of demagnetization. So that means if you consider this as a separately excited machine, there is a separately excited machine. So you have a variable resistor in series with the field winding. So changing this R, I can control the field current and the number of turns is fixed. So that means I can control the magnetizing ampere turns. So by increasing the magnetizing ampere turns, I am cancelling the effect of demagnetization. Okay. So let's do one more quick problem and then I'll wait for your doubts. So this is one more example problem I'll be showing you on board. So the example problem is like this. So this is example 18. This is again borrowed from the BL Tereja example 27.7. So electrical technology volume 2 by BL Tereja. And you can see example 27.7. This is the same thing. So the question is given like this. So the given data is 22.38 kilowatt is the output rating. So this is the output rating of a motor. So this is the first point of data that is given. Then I have So V is 440 volts. And then number of poles is 4 poles. And then the winding is wave winding. And the armature conductor has 140 commutator segments. This is just another way of giving the angle. We'll come to it. Full load efficiency is 88%. Shunt field current is 1.8 amperes. ISH is 1.8 amperes. So I'm just writing down all the given data. Brushes are shifted by 1.5 segments. So that's it. See, for 360 degrees, there are 140 commutator segments and the brushes are shifted by 1.5 segments. That means the magnetically neutral axis is shifted by 1.5 segments. So from that, I can calculate the mechanical angle, how much they are shifted. So the question, what is to be found? Ampere turns causing demagnetization per pole. Ampere turns causing cross magnetization per pole. So this is what we have to find out. So this is very simple thing. So now the thing is the shunt field current is given, but the armature current is not given. So how to find the armature current? So for that we need to simply draw the diagram. So let me draw the diagram of the machine. So this is the shunt. Basically we are talking about the motor. So therefore input will be the supply. So this is 440 volts terminal voltage. So with that 440 volts terminal voltage, the current in the shunt field is 1.8 amperes. This is given in the question, ISH. And what else is given? Under full load, the output is 22.38 kilowatt. So if the output is 22.38 kilowatt, so what is the full load input? That will be 22,380 watts divided by 0.88 because efficiency is given, full load efficiency, that is 0.88. So if I do this calculation, then I will be getting the full load input of the machine. So let me write that. 22,380 divided by 0.88. So this is 25,432 watts. So that is the input here. So 25,432 watts. This is the P in. So now I have P in and voltage. So I can find out what is the current here. So how much is the current? So just input power divided by 440 volts. So that will give me 57.8 amperes of input current. So now because this is 57.8 and 1.8 is going to the field, so remaining current going into the armature, that is how much? 56 amperes, because it's just the Kirchhoff's current law I apply here. So therefore finally I get armature current is 56 amperes. But then what is the armature conductor current? There is nothing but armature by number of parallel paths. So number of parallel paths is 2 because wave winding, it is given here the data. So if it is wave winding, then I'll get 56 by 2 So that will be 28 amperes. So next thing I have to find the theta m. So there are total for 360-degree segments. So therefore, if 1.5 segment is a shift, how many degrees does that represent? This is what is the question. So simply cross multiply. So I get 360 multiplied by 1.5 divided by 140. This is nothing but theta m. So that is 3.86 degrees. So let me cross check that. 360 into 1.5 divided by 140. Yeah. So this is theta m. Now I have all the things available for me. So now I can directly go for the final formula. Ampere turns causing demagnetization per pole is nothing but theta m by 360 multiplied by Zi. So that will be 3.86 divided by 360 multiplied by number of conductors 840 given in the question. So 840 and the current is 28 amperes. So this will give me the ampere turns. So this somehow comes out to be 252 ampere turns. Similarly, ampere turns causing cross magnetization per pole will be Zi into 1 by 2p minus theta m by 360. 840 into 28 into 1 by 2 into 4 minus 3.86 divided by 360. So again this calculation comes out to be 2688 ampere turns. So thus we have solved the problem. So I hope you have understood something in today's lecture. What is the effect of armature reaction and how we are calculating the armature reaction causing demagnetization and cross magnetization. So I hope like this is the end of the time, so I'm going to end the class. If you have any final doubts, you can ask in the next lecture. So I hope this will be useful for you. So let's meet on Thursday for the next lecture.